Hello, everyone, and thank you very much for joining our podcast. My name is Ivailu Vasilev, and I'm the CEO of Astron Drive Technologies. And we're joined by Nelson, and he's the head of our warp drive research. So, we were able to publish one very important article in Classical and Quantum Gravity, which is one of the most important journals in the field for the warp drive research and general relativity. It took us about 9 months to publish there. It took 9 months for the different referees to check our mathematics, and it is a really exciting article because we are um, looking for the thermodynamical properties for the matter which is involved in the warp drives. We're the first one to figure out how to do it, and it's super exciting because the previous time when similar work was done, it was for the black holes done about 60 years ago by Stephen Hawking, who was able to figure out the thermodynamics of the black holes. In the same way, right now we're able to figure out the thermodynamics of the warp drives. So very important research, and we cannot wait to share it with you. So Nelson, please go ahead and let's start.
Hey everyone, happy to be here again. So yeah, it's been a long time and also uh, a long walk to get here. And as Ivailo just said, this is a very nice result. It's like well, as far as we understand, is the first article that is getting involved into the thermodynamics of this type of systems. And if you see, we're calling this time warp-based bubble and not warp drive. And we'll get into that later to explain what that means. But what is more important here is that this works is we work on warp-based bubbles and non-trivial lapse functions. And we want to see what happens with matter when we work on this type of system. This was published early this year, and what we mean by non-trivial lapse function, basically, this is what we mean. This question here shows you the typical, the canonical Alcubierre's warp drive. As you see, this is written in the Cartesian coordinates, and you have the usual thing. You can have a minus or plus sign here. That depends. That you can encode that into the beta function, and the beta function is the shaping function. In the case of Alcubierre, this is a very well defined function, and we want a more general result, so we want to leave it as a beta function, and it is depending of y and c components too. So we're warping here in the x direction, and this is Alcubierre's. But what it is additional here, and this is nothing really new about this metric, is that we have the lapse function. The lapse function, which is usually taken into one, and most works related to the warp drive research, but it's a natural part of the ADM formalisms that was used to formulate the warp drive mechanism by Alcubierre. So most people work with alpha equals 1 because it's simpler, and it does not give you any great interesting features if you only consider the energy density of the system. But as it turns out, and because we found out before last year that this in order to obtain a non-trivial warp drive, you need an isotropic matter. Well, as it turns out, if you include the lapse function, you enrich even more your description of the system. So we wanted to work more with the alpha and want to see what happens. But what happens first was, like, if you include this alpha here, you get Einstein's equations to be horrible, really horrible, and it's very complicated. So what we figure is, okay, let's start, or let's figure some other system that will retain the same geometry relations between matter and geometry, but that maybe can lead us to a more simpler system of equations. That's basically it. And with that in mind, we know because out of experience, you know that spherical symmetry is a great place to look for simpler system that can describe your 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 mechanisms for any type of metric or you're working with. But what are the changes? What changes that we did is okay. Let's let's construct a new metric, which is really now introduced in this article. We introduced it before in another article, and this metric you have it in spherical coordinates. So you have like the angular part, which is the solid angle of the system, and you have a warping in the radial direction, right? So basically, what's saying, well, you have some distortion of space-time that is going on in the radial direction of the system. So, and this is why we don't talk here about warp drive and talk about warp bubble, because in that sense, this is telling you that with this metric, we're going to work a system that really is centered at, let's say, at some point, arbitrary point, and is there is the radial direction, as you know, is any of these directions is very arbitrary. So basically, we have is that you're warping in any of these vectors here. So you're warping in the radial direction. It's like expanding wave or something, if you wish. It's expanding or contracting. It doesn't matter really. It depends on the sign here, and depends on the shaping function here. So you have a beta function, and this beta function is going to tell you the form of shaping function is going to tell you how this distortion that is expanding or collapsing, or maybe we can make it expanding, oscillating, is going to be there. So if you say that and you say you have a completely different system, apparently, but the truth is, like the system retains all the features that we are interested about warp drive, which is that is it is asymptotically flat, stuff like that, which means basically that this beta is zero when you move far, and this it leads you back to a flat space-time. Also, it describes a bubble, right? And it has the same like frontier relations, we can say, between what space-time and matter, how they should couple. And so with this, we can have a description that is going to lead us to a better understanding of the physics, but also dealing with simpler equations, and you'll see how simpler they are. So, but this is not new. The new thing about equation 2 is that we add the lapse function. We want to know what happens when we add the lapse function, and we want to work it out all the equations. So that's what we did. So basically, our the parting point is equation 3. We have a very generic lapse function alpha and a very generic beta function, right? And we plug that into Einstein's equations. And of course, we know that we want to couple these. This is Einstein's equations. So we want to couple this with a energy momentum tensor that is more or less general, right? So we're working out which energy momentum tensor is allowed when we have a Einstein tensor, which is defined by this metric. You plug this metric here. This is a lot of derivatives and combinations of these metrics. And when you have the alpha and beta general functions here, well, what is it that you obtain as G mu nu? And then what that allows you to have as an energy momentum tensor? That's like the most high level question that we are asking here. And what you obtain is this. It looks ugly, but really, trust me, it's less uglier than if you plug alpha into the Alcubierre's original warp drive. In here, we have these are the components of the Einstein tensor. And although they look very ugly, the truth is like they are not all independent, and we can work this system out more or less easy in an easy way and obtain a more relaxed system. Also, the energy momentum tensor, which is going to describe everything in the matter related in your system, we plug the most general one that we can. In this case, we have, of course, the energy density, and we have pressures. What pressures do we have? Well, we have tangent pressures and radial pressures. And radial pressures, let's say we have this is your like a central point, arbitrary already, and a radial pressure is a pressure that goes in this direction, and a tangent pressure. And if you have like your a sphere here, and a tangent pressure is a pressure that goes, let's say, in this direction here, like something like this, right? And well, you have this, so that means that you have anisotropy in the system. And additionally to this, we have these two terms here. And these two terms are terms that are going to tell us if we are allowed to have heat into the system, heat fluxes. So these terms are going to be terms that are going to be, we can say, outside of the diagonal, are terms that might be related to dissipation in the system, okay? But what happens? Well, what happens is like we are saying, well, this is the most general energy momentum tensor that we can plug here, where we don't know if we are allowed to put all this together. We just plug all this, and because of equation 6, we will know if all the things that we put in the T mu nu are really allowed or not. And basically, as it turns out, you work everything out, and you get a lot of nice results. And let me show you the results. Let me go straight to here. The results are this. This is like the main thing here, and then I can show you a couple of plots. One of the first is this one, equation 16. Equation 16 is the energy density. And as you can see, the energy density is quite different to Alcubierre's. I don't know if you remember well, but Alcubierre's has something like this is equal to minus some derivative here square, right? Plus something square. So you have a minus sign here that you can get rid of this. It's impossible. But we find out that the truth is like this possible because the minus sign is incomplete. Let's say right. The framework it was incomplete. But in this case, we don't have that. You have something that is quite different. How the energy density depends on beta, and it's positive. It could be negative. It depends on beta all the time, but it's positive, and also depends on alpha. Although this dependence on alpha was always present. In the case of Alcubierre, if you plug alpha, you obtain also something like this with the minus sign here. Well, in this case, we have the alpha here. It's there. We expected that alpha there. That's one thing. And we can talk about this energy density later because this is not the end of the story with the energy density. But what the other thing that it was very nice to find is this set of equations. This set here. This set of equations is very nice. And let me read you very quickly these equations. So here you find this equation is the one that is already showed you. And this other equation is telling you something about the pressure, the radial pressure of the system, and you see how complicated is the dependence with alpha and beta. And also this equation here is telling us how the anisotropy here, this delta is basically a difference between pressures, right? Something like this. So, and my point is like, okay, that's nice. You have all this. But what about the Q? The Q that we put at the very beginning, and we ask ourselves, well, is this Q allowed by the Einstein's equations? Well, it is. It's here. You see, it is here, and it is allowed only because alpha is not 1. Because if alpha is 1, it means that this derivative here is 0, and that will imply, right, if alpha is equals 1, that implies that Q is 0 always. So the only way that is Q is non-zero is that you have an alpha that is non-trivial in the system, and this Q, which is the heat flux in the system, is directly related to how is the depending of a part of the gradient, the radial gradient of this alpha in the system, and that's a great result. That's a great result because it tells you that you can have heat fluxes that are related to the alpha, which is related to how the clock ticks between observers or two different observers outside and inside of the bubble, right? When you have like in the asymptotic limit, you have a clock that is ticking differently from the one that is inside the bubble, and the heat flux is related to that. It's a very interesting result, and of course, we're talking about heat fluxes here. So heat fluxes are related, directly related to the shears of the system, but to the temperature and the entropy on the system, which is something that we're working right now about how exactly this relation goes, and we already have some results that we aim to publish very very soon. But basically, I think this is the main purpose of these articles. I can show you a bit more because this was one of the first articles who will start working on solution of these equations. So you see here we have 4 equations, and these 4 equations are very complicated, but there are differential equations that are coupled, which means that you have a lot of things here that are here too. That's basically what I mean by couple. And so this is a big deal. Every case has its own issues, and we wanted to solve it numerically because essentially analytically it's not possible. And to do that, we just, in fact, you need to give for people that understood better equation for state for the system, which is a relation between the pressures and the density of the system, and a relation between the anisotropies and also the energy density of the system with some constants. And why you choose this? Well, there is a whole reason here of simplicity that is related to what we expect of this system to behave. And if you work that out, you get numerical results with nice things like this. And in here, this is only plot I want to show. You see in time, because we plotted in time, you can see here better. That is for several times. Each one of these curves is for several times. You see that this is the how is the form of the shaping function of the beta. So which just tells you how is this barrier, that this distortion is the right word, that construct or forms the bubble, right? And also you see how the alpha is here, and how it changes time, and also how is the heat in the system. And you see how they evolve in time, and also how they behave in time. And it's very nice. There is a lot to say here. We said we said all that the conclusions about these plots in the article. If you want to read the details, please go ahead and ask as many questions as you want. But the main point here is like, yeah, you have an alpha here, and that alpha is telling you how your fluxes are going to behave in time and in space. This is a distribution. You see, this is a distribution. Here you have space, and each curve is a space It's a time distribution. So you have a distribution, it's like a region here where you have negative heat fluxes, and the region here with positive heat fluxes, and so on. And I think that basically this is what I wanted to share with you about these new results here.
So this is very interesting. So can you please share a little bit more details why exactly we are doing that? I'll give my opinion, but please keep me honest. So our goal with the warp drive research is not only making sure that it's possible, but we want to design lab experiments. Because of that, we're going through all this pain. So in the lab experiments, we can do several things. We can use electromagnetic fields, we can use heat fluxes, we can use some complex matter. And because of that, we want to include all of that in our frameworks, because we want to design it from the theoretical standpoint, and after that we want to make sure that in the lab we can execute everything which we're designing, including positive energy. And because of that, we're doing this all energy matter distributions and all the nice research which Nelson presented. But Nelson, again, please keep me honest, and do you have anything else to say in relation to our goal to have lab
Oh,
experiments designed?
it is definitely what you said. It's uh, there are. I think there is a combination of practical and theoretical combination. At the end, they both are going to converge to is it possible, and if it's possible, how exactly is possible? I think those two questions. One is a continuation of the other. So, as you just said, understanding and maybe even solving the problem and constructing a metric or finding a fluid or a matter distribution that can sustain such a metric like the warp drive metric of warp bubble as we speak is not enough, because it's in the lab you need more information. And that's one thing that is very important. Also, the nature of the problems that are already there and we know are, we can read those problems in a different language, let's say. So all the problems that are related to negative energy densities, or any problems that are related to infinities that might appear here or there, singularities, maybe not essential singularities, but some type of singularities, all those problems, they translate also in, like, let's say, a different language when you talk in thermodynamical terms. So in a high level theoretical way, it's very helpful to give you more insight about what is the problem we're dealing with and how to solve it. But on the other hand, and this is the main advantage probably, or maybe it's the equally advantage probably, it's like you those are the quantities that you can measure in a lab, or if those are even the quantities that you can measure in an astrophysical, any astrophysical physical observation. Those are the things that can lead you to clues what to modify, what is it that you have to manipulate in the lab to have the right matter that sustains your warp space-time configuration. So yes, both are together. They come in hand by hand. Sorry, and this is very important. And that's why I'm aiming for this description, which is getting more and more closer to some thermodynamical description, and see what else is there. And I'm very excited because the work we're doing in that direction is very new, and it's giving us very nice insights. I can't wait to share that with you guys after we can publish.
Ah, me too, me too. Nelson, very well. So I think it was a really good recording, and we discussed a really important topic. Before we close for today, is there anything else you want to say?
No, nothing else. As usual, please ask as many questions as you want, and any ideas, and share if you like the video and you want to know more about something. Just please let us know. and support us.
Excellent. Indeed, if you want to keep track of what we do, you can subscribe to the YouTube channel. We have LinkedIn page. We have very nice website. And also, if you want to really support us, you can become our Patreon. The link is in the description. Having said all of that, thank you for staying with us, and let me wish to all of you to have a very nice and successful day.